In this video, we're going to look at how we can actually calculate the energy released in a nuclear process and why it is so big. Now, in order to do that, we need to use a very important equation that Albert Einstein came up with, and this is E equals mc squared. It might be an equation you're familiar with, but never really understood the implications of. Now, looking at this equation, E equals mc squared, what was revolutionary about it is that it related energy and mass. So if something has more energy, it actually has more mass. Because energy and mass are equivalent. So looking at this diagram here, we have a helium nuclei which has a mass of 4.0026, and that's measured in something called atomic mass units. Sometimes when we're talking about things like individual protons and dealing on the nuclear level, it makes sense to use a scale that's a little bit easier to work with. So that's where this atomic mass units came from. If you look on your data sheet, you'll notice that atomic mass unit, you do have a constant. It's equal to 1.66 times 10 to the negative 27 kilograms. So you do have that relationship on your data sheet when it comes to your constants. But anyways, getting back to this equation, E equals mc squared, we can look at these two different situations. We have a helium nucleus, which is 4 nucleons, 2 protons, 2 neutrons. Then we can actually look at the mass of these individual nucleons, and we see that it's larger because individual nucleons have greater amounts of energy. So according to Einstein's equation, they must have greater amounts of mass. Now, why is that important? Well, it comes down to what actually holds the nucleus together. If you think about two protons, they're positively charged and they should be repelling each other. And in fact, they do. However, there's another force at play called the strong nuclear force. This is the strongest fundamental force that we have, and it acts on a very, very small scale, across femtometers. So very, very tiny, only between neighboring protons, but it binds them together. So there's a value here, this binding energy, and that's what is missing when this nucleus forms. So we have the mass, but there's also this energy required to bind that nucleus together. So we can actually calculate the value of this binding energy. It's the difference in mass between the individual nucleons and the mass of the total nucleus together of our helium-4 nucleus. So we can look at these values. The individual nucleons are heavier, 4.0, clean that up, 4.0330 minus 4.0026. The difference between them is 0.304 atomic mass units. So we're missing that much mass. Now, we're going to use Einstein's equation E equals mc squared to convert this mass into an actual energy, because in this situation, it's that binding energy that's actually holding the nucleus together. So I want to deal with kilograms when I'm dealing with E equals mc squared. So I'm going to use the value on my data sheet, 1.66 times 10 to the negative 27 kilograms, which is equivalent to 1 atomic mass unit. So I have a mass of 5.05 times 10 to the negative 29 kilograms. So that's the difference in masses. So if I go to this equation now, E equals mc squared, I can take that difference in mass in kilograms, 5.05 times 10 to the negative 29 kilograms. It says it's multiplied by the speed of light squared. So that's going to be a very large number. So I end up getting 4.54 times 10 to the negative 12 joules. Now, that's in joules. When we're dealing with energies on the nuclear level, one thing you've noticed probably from the fission and fusion slides is we deal in electron volts. So I can divide that by my constant. So I look at my formula sheet. 1 electron is equivalent to 1.60 times 10 to the negative 19 joules. 1.60 times 10 to the negative 19 joules. So I'm just going to go all the way up here now. That binding energy is equivalent to about 28.4 mega electron volts. So that's the difference. And that comes from the difference in mass between the individual nucleons, which have more energy than the bound nucleus. And that energy goes towards binding those actual nucleons together. Now, this binding energy is important, and it actually helps us to understand what type of atoms are going to undergo fusion and what types of energy are going to what type of atoms are going to undergo fission. It's constantly a battle between the electric force and the binding energy. So that electric force wants those protons to be pushed apart. The binding energy holds them together. Now the binding energy only acts over very small scales. So again, it's just the neighboring protons. So we can still have protons on the edge of the nucleus that want to repel each other. So what happens is the atoms get larger and larger. We reach this point where now that electric force is becoming larger than our binding energy. And if that happens, that means that these atoms are becoming less stable, and that electric force is going to start to want to push them apart because that binding energy is not strong enough to overcome that electric force. That's why when we get down here to uranium-236, it's very unstable and undergoes fission because that electric force is greater than the binding energy. So it splits apart into smaller atoms. The sun can fuse things together up to copper. After that, it becomes unfavorable to undergo fusion because that binding energy now, the electric force is becoming greater than that binding energy. So it's not favorable for fusion to occur after this point. Now, the binding energy is also related to something called mass defect. Mass defect is the difference in mass between what we started with and what we ended with. So we're going to go to this example now with fission, and we're going to look at the mass defect. Now, again, according to Einstein's equation, if we have a difference in mass, that difference in mass can be converted to energy, and that's what happens in these fission reactions, in these nuclear reactions. That mass defect, the difference in masses, can be released as energy. So my mass defect is just my mass before minus my mass after. I have some masses here, some more precise values in AMUs. And I can find out my mass before and subtract my mass after. And that's my mass defect. So in this situation, my mass before, I have my large uranium nucleus plus one individual neutron that I shoot at that nucleus. And then after, I have my barium, krypton, and I have 3 neutrons. So that gives me a difference of 0.18 atomic mass units. Now again, we're going to use Einstein's equation, E equals mc squared, to find out what that mass defect is equivalent to as an amount of energy. So I'm going to multiply by 1.66 times 10 to the negative 27 kilograms for 1 atomic mass unit. And I get 2.988 times 10 to the negative 28 kilograms. So when I take this E equals mc squared, that mass defect, the mass that is missing from before and after, is going to be released as energy. 2.988 times 10 to the negative 28 times the speed of light squared is going to give me 2.69 times 10 to the negative 11 joules. Now again, typically we like to deal with electron volts, so I divide by 1.6 times 10 to the negative 19 joules. I get 1.68 times 10 to the 8 electron volts, or 168 mega electron volts. So that's the energy released. And it's directly related to that mass defect, because according to Einstein, mass and energy are interchangeable. So in this situation, that mass defect, the mass that is missing from before and after, has been converted into energy and given off as energy. And that's where that energy comes from in nuclear reactions.